Well, good afternoon, everybody. And this is talk all about stardust, which may seem like one of the least interesting bits of the universe, but actually, I think it is probably one of the most important, as we shall see as we go along. There's also an excuse to show some very lovely pictures of some interesting phenomena. And the first one that we're going to look at is the zodiacal light. If you have a really clear sky, then you can sometimes see down towards the sunset, building up at an angle away, the pillar of light coming up from the direction of the sun up into the sky. And it will come up at an angle depending upon where the plane of the ecliptic, the plane in which the planets orbit the sun, is aligned. So this image is absolutely beautiful one, captured from La Silla in Chile, and you're facing west just after sunset. Clouds are all out of the way, and you can see where the sunset light was, and that zodiacal light as a kind of pyramid of light coming up with the stars behind. There's another fantastic picture of it here with these amazing pinnacles of stone in the foreground. It just gives it that lovely spooky appearance. Also got a couple of planets visible in the same plane here, look. So the sun's gone down here. Here's the zodiacal light coming up at a slight angle. And we've got Jupiter here, and I think this one here is Saturn, in the same direction as this line across the sky where all the planets live. This, of course, is our galaxy, the Milky Way, going across, looping across the sky. So what's this phenomenon is caused by is dust in the plane of the solar system. So all little tiny bits of dust all orbiting around the sun in the same way that the planets do, and pretty much in the same plane. The second phenomenon, which is actually caused by the same thing, is the gegenschein. And as a German word, gegen for opposite and schein for light, it's an opposing light that you see diametrically opposite the location of the sun in the sky. And so if you see this faint patch here, this is the gegenschein against the background of stars. And if you're staring at that, then the sun is directly behind your line of sight, blocked by the Earth. And so this is also the result of the reflection of the sunlight back off more of this amazing interplanetary dust in the plane of the solar system, and it reflects back off the dust in this direction opposite the sun, because the particles have the property that, like a mirror, they tend to reflect more of the light straight back to the source. And so if the sun's directly behind you, then the particles are the brightest. And you can imagine them all like little tiny disks similar to the moon. So in this configuration, the moon would be full because the sun would be directly behind you. And so you're looking at the fully illuminated side of the moon, and you're not seeing any of the dark side. And the same's true for these little tiny dust particles. You're seeing all of the fully illuminated side, and you can't see any of the non-illuminated side. That's why they're at their brightest when they're at this position. At other positions in the sky, less of the light is being reflected back in your direction and scattered to your eye. So just like the zodiacal light. It's light coming back to us from this interplanetary dust, and it causes this bright spot in the sky directly opposite the sun, again lined up with that ecliptic plane. This was first described by a French Jesuit astronomer back in the late 1600s into the 1700s. There's very few people ever observed it. You needed to really have excellent skies to be able to do it. I've never seen the gegenschein. It's something I would like to actually be out in the desert or something and hopefully be able to see it from there. Now, another phenomenon that also contributes to this is the Lagrange point, L2. So let's have a look at these Lagrange points. We've got the sun and the Earth here, and the Earth moving around its orbit around like this. And a combined gravity of the sun and the Earth produces this contour map of equal lines of gravity. So near the Earth, they're pretty much dominated by the Earth. Likewise, near the sun, they're dominated by the sun. But if you reach the point L1 at the right distance between the two, then they cancel out. The force of attraction to the sun and the force of attraction to the Earth more or less cancel out. And so you get this little spot here where you could park a spacecraft or indeed a cloud of dust, and it would be at least mostly stable in that position. That's a fairly obvious one. L3 over here is perhaps also fairly obvious. It's like a counterbalance point where the gravity of the sun and the Earth is all lined up in one direction. So you can imagine there's an orbital point just over here that is stable. But slightly curiously, the second Lagrange point, L2, is also on that straight line between the two bodies, but opposite the Earth in the sky. And so quite a lot of dust can park itself in this zone here at L2 and sort of hover there in a semi-stable position. And so that tends to gather in that spot, and that contributes to that brightness of that particular portion of the sky that is diametrically opposite the sun. So you get a cloud of dust here that creates some of the gegenschein, and then the rest of it is just material that is further out along that line of sight that is temporarily in that line rather than semi-permanently, which is what happens with the dust at L2. There are two other Lagrange points, L4 and L5, 60 degrees ahead and 60 degrees behind the Earth. And they're also semi-stable zones in which things can accumulate. And the Earth does have one or two asteroids that lurk in those L5 and L4 positions. They're called Trojan asteroids if they live there, and they kind of lead and follow the Earth around in its orbit. It's quite curious that the effect of all of the dynamical forces more or less cancel out at those spots. Okay, so the big question is, where does all this dust come from? And one obvious answer is that it's the leftovers from the formation of the solar system. The image to the right here is a series of dust rings around a star other than the sun out there that will go on eventually to form a solar system of exoplanets around this young star that's being formed in the center there. And you can see the rings gradually beginning to form here as larger objects are accumulating and beginning to dominate, and that's the growing of a family of planets within that dust ring. But inevitably there will be a lot of bits left over because planet formation is a very, very messy affair. Another great source of dust, of course, is comets. And comets I suppose, are larger pieces of the leftover from the early days of the formation of the solar system. They're the bits that have not yet crashed into and become part of a larger planet. And this is, of course, the comet Hale-Bopp here, seen back in the 90s, one of the best comets for many years, with its two tails, its dust tail in white and its ionized blue tail here, where electrons have been knocked off the atoms, and so they're electrically charged and deflected by the sun's magnetic field, as opposed to just blown backwards by the pressure of the solar wind. And all of these dust particles will gradually go into solar orbit and contribute to that, both the zodiacal light and the gegenschein. We can see that process in action also on the more recent photograph from Comet 67P, Cherny-Murnoff-Gerasimenko, where the Rosetta mission went up close and into orbit around the comet and took this amazing backlit photograph of the comet in the process of outgassing, these jets of material emerging from the comet in different directions and creating these outbursts. And of course the material from the comet will go into its tail and also then go into adding to all of that dust around the plane of the ecliptic, the plane of the orbit of the comets and the planets. But another source of dust is the breakup of asteroids, and it's an artist's impression of a collision between two asteroids, and this does happen from time to time. And of course, a very violent process. Everything in the solar system is really moving at quite high speed, so you do tend to get high velocity impacts, creating shattering blows and blowing material in every direction. And some of that will then just go into orbit and become part of the asteroid belt and part of the contributing factor to all of the rest of the dust in the solar system. Other bits of it will fall down into the inner solar system, perhaps to land on Earth. And a very good example of that happened around 460 million years ago. This is a photograph of a cliff showing banded layers in the geological record, where suddenly the number of meteorites went through the roof. And this was all caused, as I said, 460 million years ago by some event in the asteroid belt. If we look at the amount of infalling material, we reckon to get about 40,000 tons a year at the moment of infalling space dust coming into the atmosphere as tiny little particles up through meteorites and fireballs, bringing larger amounts in. But if we plot the number of impacts that we know about over time, we get this graph. And you mustn't be fooled by the fact that it seems to get fewer as we go back in time here. This is the age of the Earth from 4,000 million years ago through to now. The reason we have more impact structures now is because they get rubbed out by erosion and weathering and by other geological processes. So we get a very biased view of the fact that there are more young craters than old ones. In fact, the number of impacts was greater in the past and is falling, which is not what you get from this graph if you just looked at it naively. But there's this massive spike here 460 million years ago where the number of impacts went through the roof. And the impactors were all of one type. They were all what we call L-chondrite meteorites, various different sizes, but all of the same overall chemical composition. And there's so many of these L-chondrites, they're actually 38% of all the meteorites on Earth are this particular type. And the mass of them came to Earth 467 million years ago, as dated by radioactive isotopes, looking at uranium to lead decay, argon decay, and other chains, all give the same answer to within around about 200,000 years, which is the sort of level of accuracy of these radioactive isotope dating. And we think that the parent body of all of this is asteroid Flora. It orbits only just beyond the orbit of Mars, and these are radio images of the shape of Flora that have been obtained actually by the Arecibo radio dish, which sadly is no more, bouncing radar pulses off it and managing to create radar images. 136 kilometers across its long axis, and a nickel iron core with silicates on the surface, and responsible for at least 13,000 of these fragments that have all come from the chemically similar L-chondrite family of meteorites, known as the Flora family. We've got, 13,000 asteroids that we know have this same composition and share similar orbital characteristics. So it seems that Flora is the largest member of this family of about 13,000 separate asteroids, and they all have the same composition as these L-chondrite meteorites. Flora is about 80% of the total mass. The next largest one is Ariadne, and that's 9%, and then Gaspara, which was visited by the Galileo spacecraft, is another one. So we think that there was a larger parent body, possibly a small planetoid, in the process of growing and became shattered and blown to pieces. And we see the resulting chaos and fragments out there in the asteroid belt, and the huge rush of material that all came to Earth around about the same time. It was responsible for a significant extinction event, in fact. Now here's another image of a protoplanetary disk around another star here. We've got a simulation on the left of what we might expect from our physics for a planet forming in a disk around another star, and an actual photograph of the process going on, showing what looks a bit like a spiral galaxy, but it's just a spiraling of the material in the protoplanetary disk. So a very thick amount of dust and material going on to form planets, but also spiraling into these structures. So why do we get these spiral structures, and what's going on? Well, there's an effect called the Poynting-Robertson effect, which affects everything, but it particularly affects dust particles by far the most. Because there are other effects that are more significant for other sizes of object. What happens is that dust particles that are orbiting around in the solar system are forced to gradually spiral in towards the sun, and it's the effect of sunlight on them. It causes them to lose angular momentum and thereby fall onto ever decreasing orbits, therefore spiraling in. Large particles, it's much less significant than it is for small particles, and that's because large particles, the larger something is, the more mass it has per unit of surface area, and this is all about the surface area catching the sunlight. But also because of this spiraling inwards, eventually the material, if it doesn't hit a planet first, then it will fall into the sun. And that's why the fact that we see the zodiacal cloud at the moment means that it is continually being refreshed. So it's regenerated from the comets and asteroids. But let me try and explain why sunlight causes things to fall into the sun. It's a little bit complicated, but I've got some diagrams, and we're going to first of all try and answer the question, where is the sun now? And you might think that's an entirely trivial question because you can just point at it, but you'd be slightly off actually. So here's the Earth moving along its orbit and the sun here. And we know that sunlight takes 8 minutes and 20 seconds to cross the gap, okay? 150 million kilometers, one astronomical unit. So what happens is that our beam of light leaves the sun here and sets off towards the Earth. But of course the Earth is moving, so a little bit later we have this situation. And excuse my very rough diagram, here we go, and you can see the Earth is attempting to move in a orbit rather than a straight line, so the direction of movement is changing as it moves around the sun, and the beam of light comes along and hits the Earth. Good, well that's obvious, isn't it? And it's taken 8 minutes and 20 seconds to do so. But where's the sun now? Well, actually it's over there. It's at right angles to the direction of the orbit, assuming we're in a nearly circular orbit, which is what my diagram is trying to show. But you see it, you see the light as if it's come from this point here. We're going around the circular orbit here. The center of that circle is here where the sun actually is. But for the light beam to have hit us, it must have traveled in this slightly diagonal fashion, and that's not entirely obvious. In fact, it's a very important factor in the whole of discussing Einstein's relativity, that you have to take account of where things appear to be, and this angle between where the light appears to arrive and your line of sight gradually closes up the faster you go. So if you were orbiting more quickly, you would see the line of sight to the sun at an even more acute angle than my diagram shows there. Only if you're stationary would you measure the angle as a right angle. Why does that matter? What's that got to do with dust? Well, I'll try and show it in this diagram. This is our dust particle now, and we've got the sunlight coming in from that slightly acute angle, and what happens is it hits the dust particle and it warms it up, and then the dust particle re-radiates the heat as infrared, but the dust particle re-radiates it equally in all directions from the point of view of the particle. But if you take that point of view as if you were the sun, then the sun's rays are traveling in straight, and the infrared light appears to be coming off at an angle tilted towards the direction of motion of the dust particle. In the same way you see the sun being tilted towards the direction, the sun sees your heat being tilted towards that direction, and slightly more of it coming off at an angle. Another way of thinking about it is that you're seeing the sunlight hit you more from the front. And a simple everyday version of this explanation is, imagine you go outside in the rain and you run, and the rain is coming straight down upon your head. Well, if you were to stand still, the top of your head would get wet. But if you run forwards, then your front gets wet as well, because of the rain falling in front of you, and you catch up and hit it. So you can think of it like that, the front side of the moving object gets more of the incoming solar radiation, and that very, very slightly slows it down, because it's giving it a partial push backwards and resisting the motion around the orbit. And that's why the dust spirals inwards. It gradually loses momentum and therefore falls in towards the sun. Now, this is a picture from the Cassini spacecraft of dust and the dusty rings around Saturn. and it's the day the Earth smiled, because I believe this little dot here is the Earth, and they arranged to take this photograph and tell everybody that there we are, a little arrow not marking it out, that everybody should turn their face up to the sky and smile. Of course, half the people on the Earth would have been looking in the wrong direction at that point, because they would have been on the other side of the Earth, but at least half of the population was perhaps able to smile in the direction of this photograph. But the point really is that we normally see the main parts of Saturn's rings here, but this photograph reveals the dusty nature of the E ring here, and this further outer ring here, which is associated with the moonlet called Phoebe. And this is dust in orbit around Saturn, and it too will eventually lose angular momentum and fall inwards and rain down onto the planet. You know, the rings are only a temporary phenomenon. We don't know how long they've been there, but this is just like the whole of the solar system in miniature, really, with the moons taking the place of planets and the rings being like the zodiacal dust that we have in the plane of the solar system. Bringing it back a little bit closer to Earth, though, actually a very interesting thing that I discovered in researching this was the Kordylewski clouds. We're going back to those Lagrange points again, and the L4 and L5 points, not of the Earth's orbit around the Sun, but of the Moon's orbit around the Earth. So here, instead of the Sun and the Earth, we've got the Earth and the Moon, and we have the same arrangement of Lagrange points. But it turns out that these L4 and L5 points do indeed contain collections of space dust orbiting around, sharing the Moon's orbit, but leading and following it. And it wouldn't surprise me if we don't discover the same at L1 and L2. Of course, they're a bit more difficult to observe because L1 is always directly in the line of sight of the Moon, and L2 is obscured by the Moon. But with spacecraft, perhaps we could get a different angle on it and find a way of discovering that. Now, these clouds, they were first reported in 1961 by the Polish astronomer Kordylewski, but they've only just been confirmed by observations in 2018. And there was a paper published that I was reading just a couple of months ago about this that made me get very interested in looking at all this space dust. Because one of the potential sources of this dust is that it's leftovers from the formation of the Moon. The Moon was probably formed in orbit round the Earth as a result of a giant impact between the Earth and another body that's hypothetically given the name Theia, and smashed into the Earth, blasted lots of material into Earth orbit. Part of the body of the proto-Earth and the Theia impactor merged, leaving a lot of material scattered around, most of which went to form the Moon, but could well perhaps have formed a number of separate moonlets to begin with, and eventually only the main Moon that we see today is the surviving predator, plus these bits of dust that are trapped at L4 and L5. So they would be very interesting to investigate from the point of view of a sample return mission, because we could perhaps find ways of dating them and understanding if this theory about the Moon's formation really does hold true. Now, we talked about dust rings around other stars other than the Sun. This is the coronagraph image of Fomalhaut A, and a huge dust ring around it. The coronagraph has blotted out the central image of the star here, and we've painted in a little dot just for reference. That's where the star would be, but the obscuring disk in the telescope has blotted out most of the light from the star and revealed the enormous dust ring around Fomalhaut A. Now, a few years ago, back in 2004, 2005, they spotted a lump of this moving around together, which was identified as a planet going around, or a protoplanet going around the star, and tracked its movement through this disk as it was accumulating material. But the latest news is it appears to have vanished. So either it was just an accumulation of dust rather than an individual solid object and has now dissipated, or there's been an almighty collision and the protoplanet was destroyed and scattered. Sadly, we didn't catch it in the act to see what happened. But of course, all of this space dust is very, very tiny indeed. 1 micrometer shown on the diagram here. This is some space dust collected by one of the sample return missions. The Stardust mission collected material in an aerogel. It was attempted to be parachuted back down to Earth and caught by a helicopter, but very famously the parachute didn't deploy, and so the whole thing came plummeting to Earth. But they did get some samples of interplanetary dust from it, and they have this amazing structure. You can see how there are lots and lots of little tiny globules that have all gradually stuck together in this amazingly complicated shape, with all these little tiny nooks and crannies in there. Very, very porous material, very easy for gases and molecules to find their way into these crevices. Now here's the picture I have of the disappearing planet. So there we are, 2004 and 2006, Fomalhaut B, and then it went away. Sorry, that slide was in the wrong order. But the reason I was mentioning these disks like this is because we think that the process of separation occurs according to the volatility of different materials. This is an artist's impression of a system in the constellation of Orion, V883, where the detection has been made of a young star in its T Tauri stage in the middle here with the protoplanetary disk, but they've caught it at the point where the heat coming from the star has blown away all of the volatile materials, particularly the water, H2O, out beyond the snow line. This is where the temperature finally drops as you move away from the heat source back down to the freezing point of water, and so the H2O snows out and as snow and ice beyond this, sometimes called the snow line or the ice line, around the star. And this was all theoretical in the past. It leaves the dirty, dusty, metal-bearing mineral grains behind that go on to form rocky planets in the inner part of your brand new solar system, but it leaves all the volatile ices, the water, the ammonia, the methane, all these things that are very easy to boil away, out in the cold part of the solar system. And so V883 Orionis is confirming that that separation process that we thought happens really does exist in terms of these interplanetary grains of material. Now, if we're looking out beyond the solar system, out into what goes on not on the interplanetary scale, but in the interstellar space, then we really have to rely on just a couple of sources of information. One is our intrepid spacecraft, the Voyagers and of course the Pioneers, that have left the solar system and gone out beyond now the reach of the sun's influence. The solar wind gradually slows down and loses its momentum as it's climbing away from the gravity well of the sun, to the point where the pressure from the interstellar medium overwhelms it, causes it to stop. So you get the termination shock, and then the outer heliosphere there, which is compressed in the direction of movement of the sun and extended like a cometary tail in some ways, along the path of the sun through this interstellar medium. I think Voyager 1 crossed the heliosphere out into interstellar space in August of 2012, and Voyager 2 followed through into that, made that same journey and crossed just 2 years ago in 2018. So they're now both out there making measurements and still returning data of what's going on in the interstellar space. And there were some results just the other day of them reporting that the pressure of material out there, although it's still incredibly low by earthly standards, was higher than we were expecting. So they're still doing good science. Now, of course, out there between the stars, well away from the Earth, we have a lot of these lovely interstellar clouds of gas and dust that gravity is getting hold of. Everything attracts everything else by gravity, pulls it in, and provided it's cold enough so that it's not zipping around at high speed, then the gravity can bring it together and collapse it to make new disks of material, new stars in the center, and new planets in the outer regions. And this, of course, is a fantastic photograph of the Orion Nebula here, where that process is going on, and some hot young blue stars in the center here. But look at all of the dust in the outer reaches. This is the Running Man Nebula over here. Really, they're all part of the same enormous amount of material that's scattered throughout the Orion region. Now that's caught in the act after the stars have formed, and the light from the stars is what's making the gas now shine, making it visible to us. But we also get these lovely dark nebulae. This is Barnard 68, as it says on the screen. Beautiful dark jelly bean shaped accumulation of very, very cold dust and gas out there. You can see a few highly reddened stars through it. That's because the longer wavelength red light is more able to penetrate through the dust. And so round the fringes of the cloud, where it's not quite blocking all of the light, it's mostly the red that manages to get through. So you see those highly reddened stars around the edge. But in the center there, there's enough dust to completely block our line of sight to the stars beyond. Now, this is still fairly thin. There is probably close to a vacuum by earthly standards. So very, very thin indeed at this stage, but it's many light years thick. And so it is able to add up to enough to block the light. But if you watch closely what happens to Barnard 68 over many, many hundreds of millions of years, first of all, it would shrink and collapse. And then some regions inside it would get dense enough for new stars to be born. And it would then turn into something looking a bit more like the Orion Nebula. Here's an intermediate kind of stage. This is the very famous Horsehead Nebula. And here we have another of these dark nebulae, these dark clouds, a bit like the Barnard 68, but a little more highly evolved. And one or two of these objects that we're seeing inside the dark material here are new solar systems just beginning to light up. Once they have been lit up for a while, the solar radiation tends to blow away most of the remaining gas and switch off the star forming process. But you can see how that's still fairly dense there in the Horsehead Nebula. A lot of dust there. Another lovely picture of the Orion Nebula. We're going to dive right inside it in a moment, but there is a glorious photograph of it with the trapezium right in the center, those very famous 4 stars that are primarily what's lighting up most of this inner part of the core of the Orion Nebula and blowing a huge bubble in the center of it. But if we dive right into these nebulae with the Hubble Space Telescope, we see these dark bits of nebula left over, so-called Bok globules, named after another Dutch astronomer who first identified them. These are dust where the density of the dust is sufficiently high still that it's keeping the heat out from its own core and keeping the temperature down enough that these are still contracting, whereas it's embedded in rather warmer material that's illuminated by the ultraviolet light of all of the new stars that have been born out of the original nebula. And so you find these throughout things like the Orion Nebula and others. Most famously, this photograph taken by the Hubble Space Telescope of the central core of the Eagle Nebula, M16, called the Pillars of Creation here. These enormous towers of dust and material are forming new stars within them. There's a very good example there, and a couple on the tip right up here we're going to look at, where we can really see the Bok globules forming. You can see the material being boiled away from the edges. That's the influence of all of the stars that have already lit up out of this nascent star cluster, and their light is driving away the outer layers, but the outer layers are sacrificial. The inner layers are protected by them, and so the temperature inside is still low enough that continuing collapse can happen. Now we can look at this again, but use the infrared. So on the left we have the visible picture of the pillars of creation. If we use infrared light, we can see deeper into the structure of them, and indeed right through in some cases. We definitely detect stars that are embedded within the structure here that are forming new solar systems. But if we zoom right in on the tip of the tower there, here we see these Bok globules again. Look at these around here. And on the top here, we've got this amazing structure where a new solar system is being formed right here. And the star is whizzing round, rotating, and as material is then falling in towards it, it's getting whipped up into a jet. And there's a jet going out along the polar spin axes in both directions. And here's a shock wave where the jet is impacting part of the nebula. And the more of these you look for, the more of them you can find. There's another jet coming here, look. And actually, if you zoom in on some of these other regions, you'll find more and more of these jets of material from these forming new solar systems. And so the cosmic recycling is constantly going on here. Of course, the other end of the life cycle of stars is when they run out of fuel, and very large stars will explode, and then they throw material all out around the cosmos, and that contributes to the next generation of interstellar dust. So here's a good example of a supernova remnant deep in the core of the galaxy, Sagittarius. Stars that are in the process of dying here also throw out large amounts of dust. This is V838 Monocerotis. It's not a supernova. It's a Wolf-Rayet star, a very, very large star, 40 times the mass of the Sun. And we now see the surface of this star made of helium. It's so hot that it's blasted its outer hydrogen envelope away and taken with it an awful lot of dust that is forming into this cloud around it that's being driven away by its immense solar wind. So a very extreme example of what we might call a planetary nebula. This is the Helix Nebula, a very famous planetary nebula, but a much smaller star that's just formed a white dwarf in the middle here, and we see the expanding material that's been blown away from it, surrounding it. So that'll go on to reseed and create new families of stars and planets out of this dust. Well, that's interesting. But, very curious behavior from PowerPoint there for a moment. Anyway, this was the next slide that I was aiming for. And this is a little diagram of some of those clouds that are surrounding us and our neighboring stars. So a map on a scale that you might not see very often. It's 20 light years in either direction, with us in the center. And the sun here is moving around the galaxy in the direction of the orange arrow through what's called the local cloud of material, which is all moving in a different direction, as indicated by the various blue arrows. So there's a certain amount of chaotic motion here. There's the arrows are broadly from the bottom right to the top left, but by no means all consistent. But it's definitely not the orbital direction of the sun. And a lot of this local cloud is relatively hot at 7,000 degrees, but very, very thinly spaced. So 1 atom in every 3 cubic centimeters of space. That's not as dense as it is inside the solar system, but it's still more dense than the average across the galaxy, which is only actually 3 atoms for every cubic meter. So it's 1,000 times more dense than the typical interstellar material. Now the sun entered the edge of this local cloud somewhere between 50,000 and 150,000 years ago, and it's going to, as you can see by the direction, it's going to move out again into this gap in about another 10 to 20,000 years. So perhaps the current time that we're living in is a little bit different from earlier and near future times. But again, it's going to change again as it enters this in perhaps differently structured cloud that's moving in a slightly different direction. So what's with all of this flow from this direction here, from the direction of Alpha Centauri and this way? Well, actually, this is the direction of a constellation called Scorpio, down towards the center of our galaxy. And a lot of material is moving out from that direction due to the presence of some very, very powerful star clusters of huge stars and that have formed out of shot down here, and quite a few of them have gone through their life cycle and exploded, and so there's been a series of supernovae in this direction, and that's created these shock waves that are blowing all of this gas across the line of the motion of the sun's orbit. Let's have a look at that in slightly more detail. So here's the sun moving through the local cloud. As I said, it's going to exit the local cloud and then move into the G clouds. It's moving across this line of sight from Alpha Centauri and the Centaurus cloud supernova complex down here. And all of that material is coming across our line of sight. So it's much more complicated than one might have imagined. Another way to look at that is on an even larger scale. So now that region is all in here on the sort of region out to Betelgeuse here at 500 light years away, and Antares and so on. What we think of as those local clouds is actually inside a relatively underdense region called the local bubble that is then surrounded by more dense regions. So the structure, even at these scales, is immensely complicated, with our region not necessarily being typical of all of the rest of what's going on in the galaxy. And we're only just beginning to understand all of this. If we look a little bit further afield still, we get to the Gould belt, where the stars and star-forming regions around us, around about 3,000 light years in diameter, and it seems to be a ring of stars in the Milky Way that's tilted at an angle to the main plane of the galaxy, and contains a very large number of those very hot O and B class stars. It may be that it's all part of the spiral arms and the star forming regions of the Orion arm, and we are about 325 light years away from it. That's a good job we're that far away from it, because all of those O and B class stars are good candidates for future supernovae, and so we wouldn't really want to be any closer than that. Got another diagram that kind of shows that on a galactic scale. We've got the different spiral arms, the Perseus arm, the Sagittarius arm, and this is the Orion spur, and we are just here, not far from where the Orion spur actually joins the Sagittarius arm. That's about 6,000 light years down there. This is subject of a future talk of mine, Cygnus X1, and the Cygnus OB star region. Again, a lot of very large stars and some supernovae. And there's the Orion Nebula. Look, it's all of these familiar objects, the Rosette Nebula out in the Perseus arm. So huge amounts of all of this dust and gas along the spiral arms, and we're just in the edge of it, inside the local bubble, inside the G cloud in there. So it's very, very unevenly distributed. Quite incredible how much rich structure there is to all of this. And here's a couple of images of our neighboring galaxy showing the same thing going on there. We have Andromeda 2.5 million light years away from us. The bottom image is optical and the top image is infrared. And the infrared reveals where the dust is. Again, all of this huge amounts of dust in the spiral arms. And these interstellar grains, we've managed to sample some of those. They're similar, but not entirely the same as the interplanetary particles, a little bit more compacted, but still full of all of these lovely little pockets. Why do I say lovely little pockets? Well, it's the chemist in me that knows that if you have a structure like this, it has a very, very large surface area. And surfaces in chemistry are a really good place for reactions to take place. And so these interstellar and interplanetary grains are hugely important to my understanding and to the understanding that we all gain of how complex molecules can form out there amongst the stars. Normally in outer space, there's an enormous amount of ultraviolet radiation. We're protected from it on Earth by the overlying ozone layer in our atmosphere, but the conditions beyond the atmosphere are very harsh, and molecules like hydrogen, H2 here, will get hit by the ultraviolet radiation and split up into two separate atoms. But in the presence of an interstellar grain, they can hide either behind on the far side, where they're out of view in the shadow, or more likely they find their way into all the nooks and crannies inside the grains. And in there, there's a nice protected environment. They can perhaps be split up by the ultraviolet light, find their way into the grains and stick to the surface. and they're just waiting then for another molecule to come along, and they can then react with it and form all sorts of interesting combinations of different molecules. And here is a meteorite that has come to Earth and proved this for us, because inside the nooks and crannies of this we discovered a protein called hemolithin. And hemolithin is a complex protein containing lots of amino acids all joined together, including some metals that have been incorporated within it, iron and lithium. And most of the interesting enzymes that we have in biology are metal containing proteins. And so it's quite incredible to just think that these little grains out there are little chemical factories that are producing every possible flavor of combinations of organic material with metals added quite at random. But if they produce enough of them, and then they may get lucky and produce something interesting. And in fact, one of the discoveries on this particular meteorite was the sugar ribose as well. And ribose is the R in RNA. So a very, very important precursor to the formation of the chemistry of life. So I think the more we study these interstellar grains and the chemistry that goes on them, the more we might learn about how some of those first steps along the biochemical pathway to life might well have formed out there in all of these particles. And of course, then if they fall to a fertile planet like the Earth, then the rest is history. But they will be raining down on pretty much every body in the solar system and beyond, is the implication, and that has huge significance for life across the cosmos. And with that, I shall finish. Thank you very much indeed for listening. I hope you've got the idea that actually there's a lot more to space dust than just something that blocks our view as astronomers.